Right, let's get on with it. If they're late, tough. Going?
Yeah.
Cool. Last time we met, we're going to have to wait now because I pressed the button, but it's got to set to the -1 now. I've done it. Last time we met, what did we talk about? Op-amps. Oh, we were doing poles and zeros in op-amps, weren't we? I remember. And I wrote some slides and there were too many, as usual, even though I wrote less than I usually do. So, we were about to do slew rate limiting, and we finished all the pole stuff. If you've got any questions about that, speak now. Compensation of op-amps and that sort of thing. I can kill some time while we wait for everybody else. No? Yes? The videos will be ready when I've edited them, which will be during Christmas. And then, I've given up with that Sorry Ass You player, because it's utter rubbish, and they will all go on YouTube, and the links will go on the usual place. So they will be much like Lee Ford's tutorial solutions, only not on paper, shot down as usual. So you should be able to get them in HD, or 1080i or whatever it is. 1050 or 1080? 1080. Years ago there were skis that were called 1050, it was the length to the width ratio, and they're particularly good for stunts. And I can never remember which one is which. Right then, anyway, so we've done with poles and zeros and all that, and we compensated our op-amp. And now I just want to say a little bit about what happens when you put big signals into an op-amp, or any amplifier, but we'll talk about op-amp, and see what happens to the shape of the output signal, because it will not necessarily follow the input shape. And if you've got an output which does not follow your input, then you have a non-linear system, assuming all you're expecting is a bit of gain. So we have to talk about some non-linear effects. Once I've dealt with that, we will be done with the first part of the second bit of the course, and we will move into talk about some op-amp circuits instead of what happens inside the op-amp or how it has a frequency response, that sort of thing. But they will only be first order problems, which is to say either it will be a first order circuit and a perfect op-amp, or an op-amp with a first order response and a circuit with no frequency response that surrounds it, so just resistors. If you want some second order stuff, it's in 224. Is it in 224? Yeah, okay, fine. Is it active circuits or passive circuits? Passive. Well, there should be some active stuff somewhere. So, the slew rate limiting is, I will go to the picture first, much easier. That's what it looks like. This is our signal we want to put in, and we hope to get a similarly shaped signal out, except that the op-amp can't adjust its output quick enough because it's incapable of charging its compensation capacitor sufficiently quickly. There is not enough current available in the amount of time, or there's not enough charge available in the amount of time, and the charge time is current. Yes, Q equals IT. Current is charged over time. Yes, engineering. So, we will look at the rate of change of voltage across the compensation capacitor, pretty much. And we will neglect the fact that the op-amp is full of transistors for now. We can only manage this dV by dt here, which is the dV by dt at t equals 0 for the square wave. And the shape, assuming your op-amp is first order, which of course secretly it's not, but we compensate it to make it seem like it is, you ought to get a first order system response, and the system is low pass. So we'll end up with an exponential that follows the usual shape, where tau and k is your system gain, so it's proportional to A0, which is your DC AV, and tau is proportional to your omega 1. Right, so going back to my actual notes on it, slew rate limiting is a non-linear process. If it was linear and we put in a square, we ought to get out a square. If you put in a triangle, we should get a triangle, sine wave, and so on. But actually, we'll see the sine and the triangle in a minute, and they're not. They don't look right. So this is a non-linear process, and if you put in a small V out, a small V in, you get a small V out, maybe there is some limiting. If you put in a bigger V in, you will get a bigger V out, and the nature of that limiting will be different. That is to say, you may find the slope is the same, but the limiting will start at a certain point, which depends on the size of V in. That's what makes it non-linear. If we have the same response, irrespective of the size of the signal, really that counts as linear system. Because all we're saying is it's first order, and first order system is linear, secretly. So it depends on the magnitude of VI. You will see at smaller signals, you can get to higher frequencies without limiting. Bigger signals, you get limiting at lower frequencies. So high frequencies and large signals is what usually leads you into trouble. So if you were testing an audio amplifier, for example, and you wanted to see what its slew rate was, that's to say so many volts per microsecond at the output, you wouldn't try and drive it with a kilohertz, because it can probably manage that okay. You try and drive it 50 kilohertz, and you make sure you're doing it at full power. And then obviously you'll need quite a tasty resistor, it's going to get quite hot. But you will then see you're testing it in such a way as to expose its weakness. If you give it an easy test, there's a good chance it'll be fine. So it's not like a linear system where you choose any frequency, any voltage, you get the same answer, just scale. So the cause of this, we have to charge up that capacitor, which gives us the first order response, and it's the charging up of the compensation capacitor that we are worried about. That's a bit of a simplification, but pretty much true for almost all situations. If you've got an op-amp that's not unity gain compensated, you won't get a first order response, necessarily, although it might look quite first order. So if your op-amp is an op-amp where you buy it, and you have to compensate it yourself, and you get some slew rate limiting, or you choose to look at it, it will not necessarily be an exponential response to a square input. It might have some other shape. In fact, there's a good chance there'll be some ringing, which is, everybody happy with the idea of ringing? No? Okay. That's rude. Try again. Let's assume I put this in. So this will be V in and V out, possibly something like this. And if I have some other part to it, then similarly. So this underdampness up here is called ringing. We will see some more of that in a bit. And that should tell you immediately is more than first order, because only second order and above can exhibit this resonance. There's another way of expressing resonance. So yes, we have the differential pair which sources a current into the base of what I would call T3, but the VAS transistor, and along the way it has to charge up the compensation capacitor you put around it. And similarly, there will be either a resistor in the collector circuit of the VA transistor or a current source, and that current source has to either charge or discharge the compensation capacitor as well. You will see in your head the circuit I'm discussing, or not? Yes? No? Shall I draw it? Right, draw it. This is a V plus, that's V minus. This is the compensation capacitor. This is our VAS transistor. And this is the biasing source that biases the output stage, which I didn't draw. And we have to put a current in there, signal current, in there to charge up this capacitor sufficiently quickly that this transistor can either turn off or turn on as appropriate. We can't adjust the voltage on this node without putting some charge in this capacitor. If you, for a moment, say this node is stationary, and I want to change this node, I'm going to have to put some charge in here or take some charge out. And as I turn on this transistor, this node will start to move, and the current that has to be supplied will either come from or go up there. Okay?
You're terrified.
The electronics is scary. Righty. So that's what I'm talking about with maybe you were just daydreaming, that's all. Having thoughts of breakfast. I am. Right, so it's the putting charge in this capacitor which is what we're really up to. And the bigger you make that capacitor, the more charge you'll need for a certain voltage swing. So keeping your compensation capacitor small is desirable. Of course, you have to make it a certain value to get the compensation you want, so there is some trade-off there. So the manufacturer will give you on the data sheet slew rate, and it's usually in volts per microsecond. And for the TL081 or something, TL081 is the op amp that's in the amplifier lab. It's a fairly generic late 70s JFET input. It's quite nice, dirt cheap. Everybody supplies them. Really nothing wrong with them at all. But they're nothing special, and you'll get about 8 volts per microsecond from that. If you want a flashy one that's specifically made for really high slew rate, you can get up to about 5 megavolts per microsecond, which is really, really fast, but you pay commensurately for it. So the op-amp manufacturers will be artificially increasing CCB. Well, of course, CCB is the depletion capacitance of the base collector junction. I will call this CCB as well, and I will make believe that I'm just adding one to the other because they're in parallel anyway. And the bit that I will add will be much bigger than what CCB is anyway. Secretly, CCB varies because the depletion capacitance varies, because the amount of reverse biasness of this junction varies. So making my additional bit much bigger than the CCB that's already there is desirable because it stops this variation being very important. But you don't have to worry about that. It's just something that I'd like you to know that I've got to stop somewhere. Otherwise they'll tell me off. Right, yeah, so you've got to make CCB big enough to do your compensation, but the bigger you make it, the slower your slew rate. So there is some trade-off, and you have to make a decision based on the particular design that you're working on. Happy? So this is the one that I showed you already. It is essentially a first order system. If you're wondering how I made such a lovely graph, I got an RC network, put it through Spice and plotted it. Because if you do it with an op-amp in Spice, it doesn't look like it should in the textbook because the op-amp's a bit too clever and it knows what you're up to. Well, it doesn't know. The op-amp that you look at in Spice is not necessarily made up of 3 first order circuits all bolted together. You can make an op-amp like that and it works alright. Essentially what you're doing is writing out some equations for your op-amp in circuit form and then putting them in a box and connecting things around them and making believe that it's an integrated circuit, which is not really what the manufacturer will supply you if they give you a Spice model. They give you a Spice model, it will be full of transistors and other stuff, and actually if you try to get a nice graph, it will not look like I say it will. But if you go to the lab and actually drive an op-amp and make it so you can see its slew rate limit, it does look rather first order. So you just have to accept that I cheated on this one. If you're wondering why you can't download the circuit that generates this, it's because I lied. I lied on the other one as well. Essentially, we want to know the slope of this line because that's what our slew rate is. It's the differentiation of the exponential at t equals 0. And it just so happens that if you were to look at where these two lines meet, that's not by accident. That distance there really is tau if this line crosses there. So the maximum rate of change, you just differentiate the exponential if you want to. We'll end up with kV in over tau. If you want to know how I got to the kV in over tau, that's k times v in, and it's just one divided by the other. It's a triangle. Happy? Happy, right, okay, happy then. So let's have a look at the sine wave. This one really is an op amp. Although, I also adjusted this one a bit as well. Because if you try and do this in Spice, what you'll find is the phase shift between your input and your output, because you're at quite a high frequency, because that's where slew rate becomes quite apparent. So I've phase shifted them to make them look together, because that's how you see it in a textbook. If you're looking at it in the lab or in Spice, actually you'll see there's essentially a time shift between red and blue, but I want to make it consistent. So this is the slewing bit. So this line here, the slope of that line is the maximum dV out by dV by dt that you can manage. And for this bit of the sine wave, we need more than that, slope of that big and slope of that. So you don't make it all the way up as fast as you want to, and as a consequence you miss out a bit at the top as well. And this is quite normal for a power amplifier. If you were making some laboratory amplifier for something, or a guitar amp or whatever, and you were driving it at a very high frequency with a big input voltage, this is the sort of thing that you would observe. Alternatively, if you made an amplifier for some reason and you didn't attend to the amount of current that had to charge this condensation capacitor properly, you might find you've got slewing distortion at a kilohertz. Of course, if you want to drive a 50 Hz machine, no problem at all. If you want to make an audio signal, it's the end of the world, because 20 Hz to 20 kilohertz is the human hearing bandwidth approximately, as long as you don't go to corporation too much. So the bandwidth of your amplifier and its slew rate are kind of together, but they are not the same thing. Sometimes you will see written in the data sheet maximum power bandwidth, and that is another way of defining the slew rate. It's a bit iffy though. What it really means is, if you have the output signal voltage you need to deliver the rated power into a particular resistor, or load that they specify, you can get to this frequency, the maximum power bandwidth number, and you won't get slewing distortion. After that, you will. So it's really another way of defining the slew rate, but in a bit looser terms. You'll often find that on laboratory style amplifiers, which are meant for funny things like driving lamp ballasts and all sorts of. Everyone needs amplifiers for stuff. You can make up any example you like. So to get this, if you want to know the slope of that, you just differentiate. And if you differentiate sine, you get cos. I take it that's not news. Hope not. Well, another way of it is, if you put cos on here, you get that, more or less. And the rate of change of it is, so it's highest here, because you get cos of 0 is 1. Cos of 0 is 1 in fact. So your big dV by dt is Vn times omega. Happy with that? There's not much maths, it's mostly talky. So if we look at the triangle is actually very difficult for me to draw the input and the output, because they overlay each other, even when there is slewing distortion, if I go right up to the point where it starts. After that, you just get different slopes. So what I've done is I've just put the output on, and I'm at the point where the slew rate is about to take effect. So what I'm interested in now is the rate of change of any of these bits, because they're all the same. So I'll just do 5 less 0, T over 4 minus 0, and I'll get the slope of that bit. Happy? There's a fairly trivial stuff, I think, isn't it? Well, the graph starts, the idea behind it's quite important. Much better for you to be able to describe why a slew rate happens, and to look at an oscilloscope in a lab and go, that's slewing. Much more important skill to have than any other stuff. Although if you happen to know why it happens, that is also a good start. So if we had the numbers that I put on the screen, VP is 5 volts, which is middle to top or middle to bottom. And the period of this waveform is 1.6 microseconds, then you've got to have a slew rate in excess of 4 times 5, not 4.5. The dot's in the middle, as opposed to that dot, which is at the bottom, divided by the period, so that leads you to 12.5 volts per microsecond. If you haven't managed to get 12.5 volts per microsecond out of your amplifier, you won't get a triangle with the right slope. You still get a triangle with the wrong slope. So when you look at the triangle, make sure you look twice because it isn't necessarily obvious. Happy? Right, that's the end of slew rate, and it's the end of the frequency dependence inside the op-amp. Everything now is stuff we do outside the op-amp. So it's very similar to the 118 type op-amp stuff. The only difference now is that we will put in some capacitors as well as some resistors and look at some circuits that depend on frequency. So for the rest of this lecture and the next lecture, I'm just going to rattle through this lot because op-amps are reasonably, it's just derive this, derive that. So we have to go back and have a quick look at some op-amps from 118, and I'm just going to switch R for Z, and then I can talk about impedances and not resistances, and that'll make you happy. And then we talk about some, well, two circuits that are, actually it's pretty rare to find an integrator or a differentiator made for an op-amp. Usually you just put it into an embedded system and code it up in some programming language. But actually, they're really very useful in certain situations. For example, I don't know, let's imagine you make a common base amplifier and you're going to use it as a trailing impedance amplifier, and you will connect to it a photodiode to receive a signal from a laser coming down a fibre optic cable in some communication system. Entirely plausible. You will have to go to some length to bias your photodiode because you've got to put a big depletion region in there to extract the carriers and turn the photons into electrons and get the electrons out. So you need to put a voltage across it. And to make your life easy, and to make the person who uses this, it's going to be an IC that we're going to make the person who's going to use this life easier, you want the pin they connect the photodiode to be at 0 volts. So when they put 5 volts on the other pin of the photodiode, they know it's biased at 5 volts. Happy with the situation so far? Can you see in your head the circuit that I'm talking about? Right. You all need to get Google SketchUp for your brains so that we can talk without we have to draw too many diagrams. So we're going to have some common base amplifier, something like this. Yeah, I'll do. So, just suppose that this is, I'm going to take the V out and V from here. And it'll go off to something else, maybe a really fast op-amp, maybe some other single transistor type stuff. I want to be able to allow the person who uses this IC, this is going to go inside a chip, to put V bias on a pin on the outside, and then to know that this point is ground. So they know that whatever voltage they put there is the bias on the photodiode, because that will affect the operation of that photodiode in ways that we don't really need to go into. However, if I connect this to the 0, there's no chance for me to get that to ground without making the current on this resistor 0, which will switch off this transistor, which will not make it do what I want. So I will adjust this 0 to some voltage lower than the ground in order to keep this node at 0. And I will use some feedback system to make it happen. And that feedback system will include an integrator, and it will be an op-amp. So the whole thing, yeah, we've got time, might look like, off we go. Where are we? There it is, that one. Come on, internet. Do your thing. What? For the love of God, it's a PDF. Open it. There we go. So this is an excellent paper. Clever chap wrote this. We scroll down far enough. Aha! Now how do I make this full screen? So in this business here, this is grossly simplified, but it suits me for my example. This is 3 transistors all stacked together, and I do that because it helps with noise. We would discuss noise either just before or shortly after Christmas. Well, after Christmas is like February time. So this is the column-based amplifier, and this is another column-based amplifier, and they are run under the same conditions using the same resistors and so on and so forth. And I have an integrator. Now the capacitor's in a funny place, but don't panic about it. It's all right. This transistor is just there to beef up the current capability of this op-amp. So you can think of all this stuff here as just a big op-amp. And then that point are beef up across there. So I've got my resistor, my capacitor, which is what I need to make my integrator. There is no current, no photodiode current in this circuit. It's just there, so I can look at the DC voltage here, and then adjust this point until this point is 0. The reason I'll do that is because here I've got 0, and this op-amp is trying to do whatever it can here to force these two together. So this op-amp will control this transistor to pull this rail, which is my 0 rail, downwards in voltage below 0 until this point and this point are the same. So I'll make that ground. Since this column-based amplifier and this column-based amplifier have quiescent conditions, I will also make this point ground, or very, very close. And having achieved that, I know that whatever voltage I put here, this just, in case the diode dies, you have a little resistor to limit the current so you don't blow up your amplifier. This point being 0, if I put 5 there, I would get pretty much 5 across my diode. So sometimes you do want an integrator, even if you're going to make it with an op-amp. There's no chance to do that with a processor. No processor is quick enough to reply or respond in the sort of timescales you need. The communication system is very high bandwidth. Right, if you want to go really, you can go and dig it up, but I don't want to talk too much about it now. It's just an example of where you might want to put an integrator if you make some instrumentation or something. So, oh yes, some standard op-amp circuits. Remember these? Don't want me to go through them, do you? Okay, fine. So all I'm going to do is inverting, non-inverting. R just becomes Z, and you can assume that Z can be anything you like made of L, R and C. So you can have capacitors in parallel with resistors, in parallel with inductors, or in series and in parallel, any arrangement as big as you want to make up whatever transfer function you prefer. Happy? I will not assume, well, in these situations I put AV in and I will make AV first order, as it was a few lectures back. If I had some capacitors here, if these weren't resistors, I would take away the AV and make it infinite open loop gain with no frequency dependence. Otherwise I'd end up in some second order situation, and I won't do any of that in this course. So the integrator is just this bit here. And we'll start off with this, and I'll just assume that you don't need to derive this because I already tested you on it last year. So you just sub in 1 over J omega C for the capacitance and R for the resistance, and out drops minus 1 over J omega CR as your frequency response. Happy with the idea of frequency response? Fine. So you can put them in filters into instrumentation circuits like that transimpedance front end that I just showed you. And you can put them into control systems. Actually, you can think of that little trick that I did with the 2 column base amplifiers as a kind of servo. But if you said to a control systems person, look at my servo, they'd laugh. Just like if you went to a physicist and said, I know quantum mechanics, they'd all laugh at you because we don't really do quantum mechanics like they do quantum mechanics. Isn't that an advert from a company? Some TV advert from a long time ago has that strapline with slightly different words. Intel, right, yeah. Well, their advertising's obviously paid off. Do you want a biscuit for Intel? That would have upset me for the rest of the day. So, thank you for getting it. Most of the time, actually, when you want to do some integration function, you won't use an op-amp. The situations where you want them are quite specific, but you ought to know roughly how they work. Usually we will say J omega is equal to S. Is this the first time that that's come up, or no? Okay, cool. In that case, I'm going to carry on with S for now, because the slide is only a finite size, the text has to be quite big, and the equations get a bit too long otherwise. So that just drops out into 1 over SCR. Now as omega approaches 0, omega goes to 0, the bottom bit must become 0, or the absolute value of the bottom bit becomes 0. So the whole thing should become infinite, which is really tricky because that means we're going to have an amplifier with infinite gain, and that's pretty unlikely to happen. Could we agree that's pretty unlikely, isn't it? Yeah, okay, fine. So actually the AV, the internal frequency response of the op-amp, stops that from happening, and the graph looks like this. So we have, green is that one, which is a straight line, and that's what we ideally like to happen. You could keep going back as far as you like into lower and lower frequencies, and it would always get higher and higher and higher. Actually, there is some point where the open loop gain becomes apparent, and when you get close to the value of the open loop gain, there isn't much open loop gain spare to perform the feedback functions. That is to say, the reducing of sensitivity to component variation, the changing input and output impedances, and all the other things that I said feedback does from ages ago. So you end up in a situation where it kind of curves and you actually get a pole, and because you get a pole you end up with a phase shift, and the phase shift is lagging. The reason I've drawn it as minus lots and lots and lots is I've started off at minus 180, because if you look at the circuit diagram, you'll find it's inverting. So I've got 180 degrees for my inversion, and then I have a pole on top of that. Ideally, of course, the phase would be constant and minus 270 or minus 90 if you prefer, plus one inversion, which is worth 180. The axis in this graph is done like this because it makes it independent of the particular situation. To produce this graph, I made an integrator in Spice out of an op-amp, what I'd made in a box, and I wrote some equations for the op-amp so that I knew what its frequency response would be, and then I just sealed it up, gave it 3 terminals, and made pretend that it was a real op-amp, even when it's not. Oftentimes you do that in Spice because a lot of the time you're not worried about some particulars of an op-amp that requires you to simulate 30-40 transistors. You just want to know what your circuit's going to get up to if the op-amp's ideal, and you'll make the assumption the op-amp is ideal. The reason you want to do that in your simulator is simulating a really, really big circuit takes quite a long time, even in quite a tasty computer. Let's assume you don't have loads and loads of GPUs sat around to do some parallel processing stuff. On the other hand, since you know that you're going to make those assumptions about your op-amp, you may as well just dispense with all that simulation, write out your op-amp equation, and remember that your simulation isn't going to be perfect. And if you want to figure out how it's not going to be perfect, then you can go and do the difficult simulations later. So the first time you start to figure out circuit design, usually make all your assumptions and see what happens in a perfect world, and then you can start worrying about everything else afterwards. So to make it so that you don't know what numbers I chose in my simulation, not that they're a secret at all, it's just it makes the graph more generic. I'm saying that 10 to the 0 is equal to C times R. So my value of resistance times capacitance, which is going to give me a tau, that's going to be 1 over tau, and give me my 10 to 0. So when we're looking at using an integrator, for the particular value of C and R, the region of integration is sort of here-ish. You don't really want too much phase shift, because ideally the phase shift is minus 270 or minus 90 plus 1 inversion. So you wouldn't want your phase shift to deviate too much. So about 3 orders of magnitude below your time constant is where your integrator looks like an integrator. You wouldn't really want to use it down here because your integrator's got an attenuation, not a gain. And at the very least, you'd probably like a gain of 1, which you get at CR, a frequency of CR. But that's what the axis is about. Are you happy with it? Yeah? No. Well, you can, if you want to, download the simulation and run it, and you'll get an axis in hertz, and I think I chose that as a kilohertz. just to give you some idea. But if you wanted to do it at a different frequency, there's no reason why you couldn't. You just change the time constant. Of course, if you go beyond the bandwidth of the op-amp, bad things will happen. It won't look like an integrator anymore. So you can't go forever. Happy? Not happy. Come on. It's nearly 10 o'clock. It's not. Right, any question on integrators? Okay then. So that's frequency domain. In the time domain, we should get an integrating function. So we just make, there's no difference here, it's just all the letters have got big now. They're uppercase rather. So we'd use the same sort of analysis that we would use for a regular op-amp. We'll say that this current and this current have to equal each other and there can't be any current in there. And that these two are equal to each other and it's all like AB got AB, fine. These two not quite equal to each other but jolly close. So if you sub in voltages for II and IF, you'll end up with VI minus V minus, where V minus is that node. Divide by R, so the voltage across there, divide by the resistance. And then you have to use IC dV by dt, which yields that lot, where V out minus V minus is the voltage across the capacitor. That's V minus and that's V out. And then you set it all equal to 0, because you can't have any current created or destroyed on that node. So this is the same analysis as 118, it's just now that there's a capacitance instead of a resistance in the feedback. So assuming V minus is approximately 0, so AB infinite, that drops down to this, because V minus becomes 0, essentially. And then if you were to integrate both sides to get V out, so you take away the differentiation and take the minus sign across, that drops out. Happy with that? All I've done is integrate 7 to get 8. The A is there because there is a constant of integration, which we don't know about. And we've got no way of working it out either. It is the value of voltage that was on the capacitor before you started. So if we say the circuit's been off for a very long time, and we know all the voltage will fall to 0, and you turn it on, and you're worried immediately about what the integrator's up to, your A should be 0. This or this A here. Why don't I choose A? It makes it sound like gain. You can call it anything you like. C if you want, but C sounds like capacitance. That term. You're happy with the idea of constants of integration, right? Thank God for that. So if, for some reason, I decided I was going to take out my vengeance on somebody who'd been in my lab by charging up their integrated capacitor before they came to work, it might start at 5 volts and then A would be 5, and unless they measured A in advance, they'd have no way of knowing, and I would wreak my revenge on them. Yes, but the integrator is not perfect. All integrators suffer from something called wind-up. Even if you make it in a PLC or an FPGA or something similar, you can still end up with a thing called wind-up. The trouble is there's no DC feedback. Well, in this diagram there is, I put RF in, but assuming no RF, there is no DC feedback between output and input. Consequently, any slight voltage here that you don't want, some minor offset, or some tiny offset at the output, keeps getting integrated and changing the charge in the capacitor. And eventually, the output voltage will saturate against the power supply. That's to say it'll get up to plus 15, or plus 5, or whatever, or down to minus 15, or whatever it happens to be. And after that, you won't have a voltage that's proportional to the integral of the input voltage. You'll have 15, or 5, or whatever. So we would like some mechanism to allow these offsets to pass, essentially, without ending up in our integration. So you have to put some gain in, or a feedback resistance, a DC pathway. Now the only trouble is, when you do this, you are really moving this pole. You are moving it this way to some degree. The amount you move it by, obviously you'd like to minimise, because when you move this pole that way, you are cutting into your area of decent integrator action, because as you move the pole, you'll move the phase shift as well. So we don't want RF to be too small. Usually it's a mega ohm is a decent starting value. Happy with that? Okay. I don't suppose we'll finish differentiating, we'll give it a go. So I've switched the C and the R. What a nasty trick. And now it does differentiation instead of integration. The analysis is the same. You'd say that II is equal to IF and that no current flows into B minus, and that B minus is equal to B plus and therefore is 0. And you wind up with minus J over the CR, which I would call minus SCR. And in the time domain, I assume that you will sit at home and do these analysis. I'm not going to bother to go through it. You end up with CR dVi by dt. So really, all that's actually happening with this circuit is the C and the R have been swapped over. Unfortunately, differentiators have more problems than integrators. The reason is you can't ignore AV always, and the frequency response of the op-amp will interact with that capacitance down there, and they will exchange energy fairly freely, and that will give rise to resonance. It will be a second order system. You will have some AV, which is first order, and you'll have a pole caused by, or a zero, or whatever, caused by, must be a pole, sorry, caused by your capacitance. So you end up with this funny looking graph. This is the bit which is a differentiation. The green line, well, it's essentially a circuit that's got a 0 at DC. When I say a 0, I mean a 0 as in a pole and a 0, but this is just a 0 at DC, which is 0 frequency. Do not confuse the zeros. Happy? Happy? Okay. So this is our SCR essentially, a minus SCR, and this resonance here is caused by the interaction of this slope and the op-amp frequency response, and the op-amp frequency response is going to be something along these lines. If you want to sketch it in, feel free. So this frequency is not easy to figure out. You will observe it by experience probably. The result of this, if I was to try and differentiate this triangle, I ought to get a square. Yeah? Trying this on the first years, I gave them, there really isn't very much time, but I gave them something like this. And a graph. I said the voltage on the capacitance is going to do something like this. What will the current look like? And it's just a differentiation thing. They all screwed it up, I don't know how. Anyway, never mind. So if I was to differentiate the triangle, I'd get the square. But there is this enormous ringing, which I just rubbed out, unfortunately. Who saw that coming? So this is the same. Let's imagine it's got ringing. It'll ring here, like that, and again there, for some reason. If I was to use a differentiator to figure out what happens with the capacitor. So this obviously is pretty bad because you'd like it to go straight up and then along. You can in fact add a capacitance across here, or you can add a resistance in series with the C to damp out that resonance. What you're really doing is reducing the bandwidth of your differentiator to sort of, or either reducing the bandwidth or you're increasing the Q, sorry, decreasing the Q of this resonance. Happy with the idea of Q? Yeah? No. Go on, Q, it's that guy from Bond. Sorry? If you increase the Q, make it sharper. Decrease the Q makes it more spread out.
So you have to think about it.
Oh, okay. My comment about bandwidth in Q was separate. You can either reduce the bandwidth sufficiently so that this doesn't become a problem, but you lose all this integrator space, or, well, you can't use that anyway because it resonates and you get that, or you can increase the... decrease the Q and make this much less sharp. Anyway, you have to be careful where you use your differentiator, otherwise you'll end up with this sort of situation. And something else that people like to complain about with differentiators, they go, they're really noisy. I know we haven't done noise, but I'm not coming back for this. It's just too far to come back. I'll get lost. If you were in this business here, you would have how many frequencies? Between 10 to the 4 and 10 to the 5. Well, it's 100,000 minus 10,000. Yeah? No. That's the number of frequencies. And the amount of noise you can get out of a particular bandwidth is proportional, well, it's essentially constant. It's proportional to something through Kelvin. We'll come to it in a bit. I've got more frequencies in this chunk than I've got in this chunk, because in this chunk there is only 1 hertz worth. Sorry, 9 hertz worth. 10 minus 1. So there's a lot more frequencies up here, and each little quantum of frequency gives me a set amount of noise. So this circuit is noisy up here and not so noisy down here. And the trouble is, its gain is getting bigger as we go up in frequency. So where there is more noise power available, it has got the biggest gain. It's not its fault that it's noisy, it's just how it is. So people go, oh, differentiators are very noisy. They are, but they're no more noisy than any other circuit that has an increase in gain at higher frequencies. It's just one of those things. If you go into SPICE and differentiate a sine in the hope of getting cos, which you will find your sine wave is covered in horrible noisy stuff, especially where it's turning. Top and the bottom is where you see it the most. Right, I finished nearly on time. So we talked a bit about slew rate, and then we talked about the integrator and differentiator. And then I spent a little bit of time waffling on about the things that are wrong with them. You'll find that if you do an embedded system differentiator, they are also fairly noisy as well, but the manifestation of the noise is a bit different. Well, it happens for different reasons. Right then, I will see you tomorrow for more of the same.